All right, this is APChem test prep level 1A. I'm a gamer. I like doing things in terms of levels. Okay, so this is just some review videos to get you guys mental jogs through the material. Make sure you know what to do, how to do it, and why you need to do it. Okay, this is going to start with some very, very basic stuff. You may watch this and think, hey, Mr. Fry, that is super easy. Why are you telling us this? Because some people need a refresher, and this is a good, just quick refresher for you. Okay, so the very first level 1A is talking about unit conversions between mass, moles, and particles. Okay? So, we have some conversions between mass, moles, and particles. Mass, as we know, is the amount of matter that something contains. The number of moles is a representation of Avogadro's number, and the number of particles can be found from the number of moles. So, first off, mass. It's in units of grams. Okay, mass is in units of grams. Keep that in mind. Moles, it is in units of moles. Interestingly enough, okay, moles is a made up unit that is very helpful for chemists. Okay, it is always going to be 1 point, not one. Are you kidding me? I'm a science teacher with a master's, and I still can't write stuff right. 6.02 times 10 to the 23rd, or 602 sextillion. Okay, that is equal to 1 mole. Okay, it really helps us count particles. Now, to get a quick little idea of how large this number is, if you were to receive 6.02 times 10 to the 23rd pennies on the day that you were born, okay, and you spent, I believe it's $1 million a second until the day you die per second. I may butcher this completely. I saw it on a video once and I'm trying to remember it. 6.02 times 10 to the 23rd pennies on the day you were born. You spend $1 million a second. On the day you die at 100 years old, you would still have 99% of your wealth left over. Okay, that is a huge number. So when we talk about moles, moles is a large number of particles. It is much easier to count moles than it is to count number of particles. We've also done the math. The average person could not draw 6.02 times 10 to the 23rd atoms in their lifetime. It would take, I think we calculated 1.6 times 10 to the 10th years to draw out that many circles. So do with it what you will, but that is a very large number. Okay, and so that ties in moles and particles. All right, now if we had 3 let's say 01 times 10 to the 23rd particles of calcium. Okay, we have 3.01 times 10 to the 23rd particles of calcium. That would be 0.5 moles of calcium. Now, if you're not an AP and you look at that and you say, Mr. Fry, how in the heck did you get that number? Well, let's look. We've got 3.01 times 10 to the 23rd particles. I know from our unit conversions right here. Why is that dot not erasing? I know from our particle conversion right there that for every 6, we're still in blue. 6.02 times 10 to the 23rd particles is 1 mole. Now, if you don't set up your conversions like that, like I do, that is perfectly fine. You can set them up in ratios. You can set them up any way that you want. This is called dimensional analysis. Dimensional analysis. And it's the way that I was brought up calculating these unit conversions. Okay, so when we do this calculation using dimensional analysis, we multiply all the numbers on the top by each other, and then we multiply all the numbers on the bottom by each other, and divide the top number by the bottom number, and we should get 0.5 moles of calcium. Okay? Now, let's look at this and say, hey, how do we go from moles or particles to grams? Okay, there is no direct conversion between particles straight to grams. Okay, you have to go from particles to moles, and then from moles to grams. Okay, we do that through something called the molar mass. Okay, the molar mass is a number in grams that tells us if we had 6.02 times 10 to the 23rd particles of that element / compound, we would have one certain mass. Okay, and that is called the molar mass. Okay, you can think of it as if I had marbles of water, so just certain, let's see if I can make this 3D. Not really. Okay, we have marbles of water, just little particles of water. Okay, and we had 6.02 times 10 to the 23rd of them. Okay, and we put them in a little sack. Let's see if my drawing skills can substantiate this. Put them in a little sack, and we said H2O marbles on it. And then we took that sack and we put it on a balance. Look at that. Just call me Leonardo DiCaprio. All right. And we put that on a balance. It would weigh out to be its molar mass of 18.02 grams. Okay, now we know that we have 1 mole of those particles. So we can say that the molar mass, if we had 1 mole of these water particles, the mass would be 18.02 grams per mole. Boom, bang, bop. That is how we get the molar mass. Now, this molar mass is the conversion between moles and grams. Okay, so let's say I have 32, make it easy on myself, 36.04 grams of H2O. Okay, I have a cup of water and I put it on a balance and it says I have 36.04 grams of water. Then I can say, well, I know that for every 18.02 grams of H2O, I have 1 mole of H2O. So, by the ratio or ration properties here, I could say that I have exactly 2 moles of H2O. Okay, and if I want to find out how many particles that is, I could say, well, if I have 2 moles of H2O, well, for every 1 mole of anything, there's 6.02 times 10 to the 23rd of that thing. And so, if I do 2 times 6.02 times 10 to the 23rd, I have 12.04 times 10 to the 23rd particles of water. Boom, bang, bop. We can convert between grams, moles, and particles. Okay? That's it. That's all you need to know for that. Now, you may look at yourself and say, well, how do I find the molar mass of anything? Just look at the periodic table, baby. Look at the periodic table, baby. Baby. Okay. The periodic table has masses for all elements. Eminence. All eminence. Now, if we have water, H2O, let's just say, well, the molar mass of hydrogen is around 1.01 grams. That's what the periodic table shows, and that's what we find on the periodic table. So if we have 2 of them, that means we have 2.02 grams of hydrogen. Now, oxygen's molar mass is 16.00 grams, roughly. And so there's 1 of them, 16.00 grams of oxygen. If we add that together, that's, oh my goodness, look at that. That is 18.02 grams of H2O, and that is exactly what we used up here. Okay, so if we look at it at the periodic table and we know our chemical formula, we can just add the molar mass of the number of that type of element together, add all of that into one sum, and that is our molar mass of that compound or element. Okay. Now you might be thinking, well, why is the masses on the periodic table, why are they not whole numbers? Because I mean, in everything else, when we're talking about elements, everything's in whole numbers. We can't like have half or 0.02 of a hydrogen atom, can we? And the answer is yes, you cannot. As difficult as that answer might be, you cannot have 0.02 of a hydrogen atom. Where these numbers come from are isotopes and relative. Is it relative? It's yeah, mass. Is it relative? I feel I'm psyching myself out here. Relative atomic mass. We'll just say relative atomic mass. There's probably a better name for it that I just can't think of it right now. Okay, so it all has to deal with isotopes and their relative abundance. Okay, so for carbon, carbon has like 3 different isotopes, I believe. Um, and actually, let me find that out for sure. All right. Through the magic of the internet, I found that there's like 5 isotopes, but only 2 that really matter. And those 2 isotopes are carbon 12 and carbon 13. Now, carbon 12 is like 98.9% of the abundance. So, like, if you had 100 carbon marbles inside a bag, 98.9% of the time, you would reach in and grab carbon 12. And then 1.1% of the time, you would reach in and grab carbon 13. Okay. Now, a lot of you guys have probably heard carbon 14 dating. Now, there is a carbon 14, but it's like 1 part per trillion percent like abundance. So you don't really need to worry about that in this calculation. So the 12 and 13, those are its atomic masses. And then we take into account the abundance of these masses. So we take the mass times its percent abundance, 0.989, and then 13 plus 13 times 0.011. Okay, when we add those together, we get 12.011, which by golly is the mass on the periodic table. Okay, so you guys need to know how to do our relative atomic mass calculations. You need to understand how and why those numbers are calculated. You need to recognize how to find the molar mass of an element and how to use that molar mass to do conversions, how to draw better stars, and then how to convert from particles to moles and moles to particles. Okay, very quick. This is very easy, breeze through material. So that is AP Chem Test Prep Level 1A.